So far, we have seen the most important neural networks. In this last section, we present several other neural networks and compare them in terms of predictive performance and number of parameters. This slide is based on the research paper above on inception. Here are three schemes representing three different versions of the inception model. Remember that we have already talked about the inception model, which is at the core of GoogleNet. Here are three different versions based on different ideas. The main idea behind these inception models are the use of 1 by n or n by 1 convolutions. Indeed, composing a 1 by n convolution with a n by 1 convolution is equivalent to a convolution with a receptive field of n by n, with additional constraints on the kernel parameters. Therefore, composing asymmetric convolutions as 1 by n or n by 1 convolutions can help reducing the overall number of parameters of the network. In the second inception module, two 3 by 3 convolutions are used with different strides. In the third inception module, two 3 by 3 convolutions are used in lieu of a 5 by 5 convolution. We have already seen this idea in VGGNet. Label smoothing is also used, which corresponds to adding a perturbation to the one-hot encoded output vector. Exception, which stands for extreme inception, is another important neural network. The idea in exception is to decouple the convolutions along the depth and along the spatial dimensions. To this aim, 1 by 1 convolutions are first applied, and then 3 by 3 convolutions are applied on each slide of the volume. This is the main difference with previous architectures, for which the convolutions always operate along the whole depth of the input volume. We can compare all CNNs we have seen in terms of predictive accuracy and number of parameters. On the left picture, you can see the top 1 accuracy of all networks, and on the right picture, you can see the relation between the top 1 accuracy and the number of operations. The number of parameters correspond to the size of the circle. On the left, Inception and ResNet are the most accurate CNN. The performance is computed on the ImageNet dataset. On the right, you see that Inception and ResNet contain a small number of parameters. The current trend in deep learning is to obtain similar or better performances while keeping constant, or even decreasing, the number of parameters. We have seen the most important CNNs, but the list is not exhaustive. Here you have a taxonomy of different CNNs, which comes from the detailed review paper below. I encourage you to go and read this paper if you want to have a really detailed and very exhaustive view on what is done in CNNs nowadays. In this lecture on CNNs, we have seen most of the architectures depicted here and the most important ideas to construct CNNs, reducing the filter size, decomposing convolution into more elementary convolutions, using 1 by 1 convolutions, using shorter connections, and so on. These ideas are important to remember if you want to design a new original CNN architecture.